let's just jump right into it. Silq. So I basically came across these here yesterday, and I haven't really read through all of it, and I'm quite excited about these because it's kind of one of the first times I see there's an attempt to do something just more than building circuits, some kind of step forward in terms of a language that to program quantum computers that is kind of trying to move away from the circuit model, which I kind of feel it's sort of the really low level, right? Like I'm not saying that's obsolete or it's going to be obsolete. I think for those kind of fine tunings or really specialized algorithms, that still is going to be the way. Especially for quantum machine learning, I think that's still going to be at the level you operate because you build models like as a circuit, right? But I was curious to read about Silq. It's from ETH Zurich, and so high level, it's kind of supposed to be more high level programming. Let's see, I'm interested to see if I can actually play with these right away, or I should just read through the stuff, because I saw this link and I was like, I gotta go take a look at these. I definitely gotta go take a look at these. Silq, so Grover's algorithm in Silq. I don't even know what Silq is though. What is it? Comparison to Q#? Code, library, examples. So I see there's ifs and stuff like that. So I wonder if those are classical ifs or... Well, they must be quantum because there's a CX, there's a C0, and then there's no C0 in here. So there must be... There's some examples and computation. Oh, you can install Silq. Okay, let's go through this. Linux, Windows. Oh, so you need Visual Studio Code. It's great because I just happen to have it. So Windows instructions, runtime check. Download a Visual Studio Code installer. Okay, but I have these. Yeah. So how do I just open VS Code and so VS Code. Okay, so this is an extension you can install directly. That's cool. It's cool. I was doing my quantum computing, the Q# competition in here. So how do I open the extensions? Control-Shift-X. Control-Shift-X. Extensions, and I search for these, and here you go, installing. Okay, cool. And then what? Run type check. Type checking now happens automatically. Okay. Run program where I can get an example. Install from GitHub. No examples. Generate superposition of zero state and a basis state. So you have an example. How the hell am I supposed to write those things though? Okay, so it's installed. How do I get how do I start a project with these? Requirements, known issues, extension settings. It's an extension, but like, is it do I have to use a Q# program or something? How can I start a project? So view command palette. So what if I do Silq, run Silq file in focus? So do I have to create a new project, but not a Q# project? So maybe where's Q#? Examples. Installing Silq. How can I run? Install the plugin. Okay, maybe in GitHub there's some instructions. SLQ. Okay, so I've got to create so just got to have, maybe it's just a file and it just runs the file, or what? Requirements, extension settings. How do I save my path to executables? So I can just maybe create a new file. We'll just try that. Let's try and run one of these examples. So file, new file. And I'll just copy. Can I just copy these? I wonder how is this going to copy paste though. Okay, and I can save it as what? As a, so I'll go here and I'll make a new folder called Silq. Get into Silq and then do test LQ, I think it was, right? Save. Okay, here we go. And now if I go with Silq, run file in focus. Oh, nice. Look at this. Okay, so there's a result and there's like that's a state vector. Nice. Okay, so I got it to run. So you kind of run files like that. Let's jump into, that's really simple. I haven't really, it's the first time I touched this thing. It's the very first time that I touched this thing. Good. So let's go for it. Grover's algorithm in Silq. Oh, nice. Okay, let me put my face away from here. Okay, so there's a there's a correspondence to a circuit. Maybe let's quickly start. So this is background, basic features. So we first introduced some basic features of Silq, variable assignment. Okay, so this equals to these. So y, okay, this is the result of Hadamard. And we have named, here we have named the wire into h as x. Here we have named the wire into h as x and the resulting wire as y. A possible state before applying h is this thing where subscript x indicates that the variable x stores 0. Okay. The line with the assignment would then result into this state. Okay, meaning that this is held in the variable y. Okay. Conditions. The following snippet performs a controlled application of the Hadamard transform if x. Okay, interesting. Compiling the snippet to a circuit yields. Okay. Grover's algorithm in Silq. Oh, that feels like complexity just went up now. What the heck? How do this? So you actually have to write things like that. How am I going to get these characters? How do you even know how to have those characters in there? I mean, you guys see better probably like these. Okay. So, okay, that's something like, that's pseudocode, right? How do I do this? Is there an actual code that I can copy paste for Grover's algorithm? Oh, that's a long one. Okay, anyway. What I was reading though is I was reading that also there's here on computation. Okay, cool. Let's go step by step, okay? We illustrate Silq and its benefits on Grover's algorithm, a widely known quantum search algorithm for a given function, blah, blah, blah. We first show the implementation and then walk through its features. Okay, so it's a function, Grover, and then, okay, it calculates somehow. I have no idea what those things are in here. This exclamation mark means it's classical. It's a classical natural number. And I guess that is, and is used, let me see if I can, if I see I can switch the pen on. Yeah, so now here we go. So this N seems to be used in here, and F is here. Okay. F preserves argument. Function consists of classical operations. Okay. So you define the number of iterations. I should choose a different color. The number of iterations I guess can stands for candidates. And it's an array of n numbers. Okay. So for k in 0n, then we iterate over each candidate, and then we kind of... Is it a superposition we're doing here? So we're doing a Hadamard on a number? On a candidate? It seems like it's... Yeah, that's like n equals superposition. Or what is this? This is the initial state. So this is the first layer of Hadamards. Then another loop where, okay, we go through... Okay, so this is this is the actual main loop. And those two pieces must be... These must be... Okay, so if this is Grover's diffusion operator, this must be the oracle. What the hell? If f canned... So this is an oracle that if... I don't know what is f, but if something, then we're phasing. But this is a quantum if, right? So this is somehow a controlled operation? I don't know. This is complicated. But it's... Comparison to circuits. Okay, maybe that's going to be better. So what are we doing here? We have if... Yeah, so this is the... Okay, so this is the preparation of the initial superposition. So this is when you have like... I was going to draw the circuit, but the circuit is here. So this is the... yeah, whatever, initial superposition. This part in here is the... What is this? UF and the inverse of UF. So this must be the oracle. But I don't know what UF is. So definitely the goal is to phase something. So you have... This seems like an ancilla qubit, and you're phasing something. Okay, and then Grover's diffusion operator. Maybe this is supposed to be... Because I'm so used to hard coding the oracles that maybe this is a more generic... So f is whatever your problem function is, right? So that's what you're kind of... That's what's giving the structure to your problem. Generic parameter and classical types. The first argument of Grover is a generic parameter n used to parameterize the input length of f. Okay. It has the exclamation mark natural, which indicates classical natural numbers of arbitrary size. This indicates it's classically known. It's not in superposition. Silq requires generic parameters to be classical, allowing their use in parameterizing types, while Silq supports quantum values of the fixed size quantum integer types. Fixed size quantum... Okay, yeah, because you give it the integer keyword. And uint, unsigned integers, it disallows quantum values of type z, containing all integers. Or n containing all natural numbers. The function body also requires n to be classical, otherwise we could not determine the number of loop iterations, which code state. To concretely recall f multiple times, as we will silently drop it from the context at the end of Grover. Q-free functions. The type f is annotated as Q-free, which indicates that f neither introduces nor destroys superpositions. What? In particular, if f takes as input a base state, then it will return a base state. A good example of a Q-free function is a bit flip gate x, which maps... That's a new concept for me. Okay. It neither creates nor destroys superpositions. So it only... Okay, so this means it only manipulates the phases of a superposition? But can it modify the amplitudes of a superposition? Probably not. It only modifies the phases of a superposition, or it just goes from one pure state to another pure state. Pure is the wrong word. It's a non-superposition, non-superposed state. Okay, so this is F. And in this case, it makes sense because it just flips the values. It flips the phases. Maybe it's even bad to just keep the circuit in mind, right? So it's even bad to keep the circuit in mind because I want to detach myself from the circuit at some point, or that's the goal of the language, I guess. But it's still can. So what is can? Can are all the candidates. Okay, so can is the superposition. Can is actually the candidate. So this is the whole superposition of is all the possible solutions? Is it? Say like 8 if we're using 3 qubits. So this would be like the 8 possible solutions. And then if f can, okay, so if this function evaluates to true for the candidates, then phase the candidates. Okay, so I kind of have to read these as run these for the values where the function evaluates as true. Okay, that makes sense. Okay. And we're not mentioning any qubit in here. That's quite interesting. There's no mention of qubits, to be honest, which is quite surprising. But Q-free functions are, this is an interesting new concept. So those are functions which do not create nor destroy superpositions. Constant parameters for Q-free functions note that while X is Q-free, it does not preserve its argument. It consumes its input. In contrast, the argument of F is notated as const, indicating that F preserves it. Oh, here. Okay, so here is const. So what this is telling us is that this function is preserving the candidates. But it's not preserving the phase of the candidates, right? Concretely consider the state, it consumes its input. Concretely consider the state where it captures the possibly entangled remainder of the state. Then running yfx on this state where f is q-free yields the resulting state preserves the original summoned expressions and augments them with an additional value. I might have to reread this. I didn't expect this to be function parameters. So what is it? What does this mean? I mean, the sum. Okay, where these captures the possibly entangled remainder of the state. What does this mean? What is the remainder of the state? So this function consumes them. For example, Grover-Diff consumes its argument. See top right box in the above code. Hence, the call in line 8 consumes the candidates, transforms it, and writes the result into a new variable with the same name. Similarly, measure in line 10 consumes candidates by measuring it. Okay, Grover-Diff. So it consumes and it. I'm curious to see what Grover-Diff does. Input state, superpositions. The status system after line 1 is V1, where f and denote the values of variables and shows variable transitions. Okay, superpositions where can holds the equal. Okay, so can holds the equal superposition of all n-bit integers. Line 4 updates the ith bit of can by applying the Hadamard transform h to it. So this is actually preparing. It's actually preparing the superposition. Yeah. Loops. In line 6 runs in iterations time, blah, blah, blah. We discussed the first loop. So that is classical. Each loop iteration increases the coefficient, thus increasing the probability of measuring the desired state. We now discuss the first loop iteration K0. It starts from state, which is okay. For convenience, it also splits its proposition into and all other values. What? It starts from state 60. I don't know what this means, which introduces variable K. I don't know what we're talking about. Well, I don't know what they're talking about in terms of splitting the state. I'm doing a quick run first, as I usually do. So just so you know. Conditionals. Line 7 runs phase pi if f can returns true. As phase pi flips the sign of coefficients, line 7 changes the coefficients. Okay, yeah. And the circuit shown previously will physically realize this by evaluating f can using UF, applying phase pi using a Z gate, and uncomputing. Okay, so there is some implicit uncomputation happening in here. But why do you even need to uncompute? Because if you hard code the oracle the way that I've always been doing it, you don't need to uncompute anything. But maybe that's then just generic. So there's a reference here. So uncomputing fcan is critical, as we'll discuss shortly. I guess this is shortly is probably leading me to here. So while the behavior of Silq's conditionals and the resulting state is intuitive, achieving it physically requires uncomputation of fcan. At the end of line 7, concurrently before this uncomputation, the state contains the value of fcan stored in a temporally variable fcan. Okay, because, so theoretically speaking, you've got the results of whether fcan evaluates to 0 or evaluates to 1. This is living somehow in your state. Now, dropping fcan, removing from consideration, is physically equivalent to measuring it, concretely measuring. So I'm trying to. It's so hard because you have to move away from the circuit perspective of things, and that's extremely hard to do. So you don't want to know whether your function evaluated to true or to false for a given run, and so you must uncompute it conceptually. Okay. Regardless, like, forget about how the oracle is implemented. Forget about whether you're just doing a multi-control set or something like that. Because the multi-control set doesn't need any uncomputation, right? But I guess this is, oh yeah, I know. Look at this, NISC for Grover for NISC machines, yeah? Grover for NISC machines. So I think this is no, I didn't want my channel. It's nice that it appears in the top. It appears even before the actual paper. I know. I think I know what this is. Okay. Come on, load. So this is, yeah. I gotta find this. Yeah, this is this. Okay. So let me see if I can zoom in with the other hand. So I think that by uncomputing, they actually refer exactly. So this is an example of an oracle. Can you just my face be example? This is an example of an oracle that is basically you're doing that. So you're if this connection, if the those two vertices have like opposite colors, then you're adding an increment to this ancilla qubit. So these kind of, you can think of these as being your fcan, right? And so you gotta uncompute that because otherwise, here you go. Yeah, exactly. So you gotta uncompute these. Yeah. So this is this part. Okay. You're uncomputing these. So this is a general approach to the oracle. You can, yeah, okay. So you can, of course, always hard code it, right? This is really This is really interesting. And this happens automatically, so you don't need to think about this. You don't need to worry about uncomputation. It's beautiful. Huh. In this case, the probability of attending is returns the correct result. As a consequence to prevent an undesired implicit measurement, we must uncompute fcan and modify its state to be unentangled with all the other clues in the system. In our case, correct uncomputation yields intuitive semantics that simply forget the state of fcan. Wow. Completing the explanations of our example, line 8 applies Grover's diffusion operator, increase the coefficient. Okay, but I'm interested in the details of the Grover diff function. And computation pitfalls. Various people can lead to computation issues. Programmers may forget to use it altogether. Indeed, it happened to me. This happened to me. I mean, this literally happened to me while working on the implementation here. Attempt to uncompute variables that are not actually uncomputable. Use wrong operations for uncomputation. Yeah, that also happened to me when I was uncomputing an S or a Z with like an S or a Z, where you should use the opposite one. Rely on variables, the inverse one, S minus one or something. So rely on S dagger. Rely on variables no longer available in the computation. I don't know. So automatic computation, preventing errors, invalid measurements. Where is the Grover's conditional measurement? Oh, there's so much to go through here. In the following, we demonstrate how the type system of Silq rejects programs with unintuitive semantics, which are physically unrealizable. Silq prevents implicit measurements as illustrated in the following example. So if you, define a function, the parameter x is not consumed. Why? So n is a classical value. X is some number, and then so you do y equals x modulo 2. And then you just return y and forget about x. It's not consumed. It's not overwritten. The above function tries to forget variable x, which cannot be uncomputed, as this would induce an implicit measurement. Silq rejects this code. Okay. Can we try this? Can we try this? So if I add this function, and I'm going to be calling return implicit mass. Is this the return implicit measurement? And I'm going to give it a, 3? And can I now Silq? See, problems window. Where's the problems window? Problems window. Ah, nice. Parameter x is not consumed. Wow. Dude, that's so cool. Oh my. The above function tries to forget variable. Okay, we know that if parameter x is constant, it need not be consumed. Why would you? So if I just change that to const Silq. Problems. Called with arguments. Oh, I'm missing something. So what is it? What is these though? Oh, it's an sorry, it's an array. So this should be something like uint, I guess, 3. Silq. Function of type cannot be called with arguments. Okay, I'm. Oh, what have I done? Is this the? Okay, whatever. I think I'm not calling it correctly. Maybe I'm missing these. No, I'm somehow not calling it correctly. Okay, but I'll figure this out later. The timing. Cool. Yeah, I think that's super interesting. Okay, we're doing this next video. Gonna build Grover's algorithm in yeah. I gotta go now. Um, wow, using consumed variable. So what time is it, by the way? Okay. Condition measurement, unconditioned measurement. Cool. I'll leave it here. That's definitely something to work on. Interesting. What else there is in here? What are the other examples? What is Silq? Grover's algorithm comparison to Q-sharp, discussion of and computation installation prevent errors. Nice. Wow. This was really unexpected. This was really unexpected. This is so exciting. Cool. Nice. Nice. I mean, it's just something different. It feels like fresh air. And that's always really, really interesting.